Okay, we start up. Actually continuing from last time. I'll just try now to use light when I use the blackboard, so the video was a little dark, you said, so I'll try to use the light when I use the blackboard. Just to recap from last time, we were solving the Poisson equation, and here I've solved it on the entire domain, you say, from one wall to the other one. Y goes from -1 to 1. So it's a non-dimensional equation. Here, time derivative equals a constant, the driving force in the problem, plus double derivative. So that's what you get from the transient problem from the Navier-Stokes laminar flow. Boundary conditions 0 on both walls, and initial conditions 0. And here now solved with an FTCS scheme, which then should give us the velocity profile. Here I have said maximum time is 3. The dimensional equation, non-dimensional equation, should have a time scale of roughly 1, so you never really know how big is 1. Here I had to go all the way to 3. If I stop at time equal 1, then I didn't get the maximum velocity in the center of 1 like I wanted to. So I had to go a little bit beyond the unity there. Also, we have a time step, which is then your choice. And I showed you last time then how to find a very simple limit as a stability criteria, not the exact one, not the correct one, but a sufficient criteria. And here, this R, the ratio delta t by delta y square, has to be smaller than 1/2. That it was the limit, and if we go a little bit above, then yes, indeed, we will have problems, and the solution will explode. So here, actually, the criteria is quite spot on. It's a linear equation anyway, so yeah, it should be okay. How to find that stability limit? I showed you last time, but we can quickly repeat it. Here you have the internal loop. So you have a new velocity based on old values. So now you check, well, first of all, we have a source term here, which we then skip. Delta t is small, he's going to be small anyway, so forget about him. And then we say the 3 velocities I have that I'm basing my calculations on, they have the coefficient here, 1 minus 2r, and these two guys, they have just 1r. If you add all these 3 coefficients together, you get 1. And that happens quite frequently for many simple schemes. So, and then we can use this method, the way of thinking. Then we could say this new calculation, he's going to be bounded between the biggest one of these 3 u's and the smallest ones. He's going to be in between. That we are dead certain. If, and you have then 2 ifs. One was the sum of the coefficient is 1. That's the case here. We can use the method. Second, all coefficients has to be positive. The r itself, coefficient for these 2 velocities, he's constant no matter what. But here, 1 minus 2r, he has to be positive or equal to 0. Aha, the limit is 1/2, which actually is the case. Okay. Any questions to this one before we continue with it? So the time step here is quite small, 0.005. You need many time steps to get to the end. You need n max 600 time step. So then the question I wrote last time, 600 time steps, and it's only first order accurate in time. Don't we risk accumulating a big error? although maybe with one single step the error might not be so big, but with 600 steps or 10,000 steps, won't we accumulate an error? Well, let's find out. Let's use a higher order method. Well, I don't need the blackboard actually, we can take it on the fly, I think. No, not that one, that one. I want to solve the same problem now using an ODE solver. First of all, I can skip this one, multiply him with 0, then he doesn't do anything, I hope. Yeah, that's okay. So now I want to solve the same problem, same equation, but I want to use an ODE solver. How to do that? Well, first of all, here I'm going to need some velocities. U equals zeros. So now I have, how many do we have here? We have J max. J max and 1. And then I call sort of my initial values. Everything equal to 0 at time equals 0. Then I call an ODE solver. What does he give me? Well, he gives me a timetable and he gives me a matrix containing all my unknowns. So now it depends how many differential equations do you have. How many do we have here? Well, hang on. These ODE solvers, they are for ordinary differential equations, not partial. What am I doing here? But the way you can think is the following. This is the original equation. Time derivative equals to double derivative in space. So now I just look at this part and say, this one, the time derivative part, I want to use an ODE solver. For the right-hand side, there I use finite difference. So there I don't use any ODE solvers whatsoever. So I look upon it at one single point. I say, this double derivative I have to create as a right-hand side of an ordinary differential equation. Hence, I'm going to have 21 minus 2 differential equations. The first one and the last one, they are on the wall. They are the boundary conditions. But everything in between, they are going to be, at each point is going to be represented by one ordinary differential equation. That's what I'm trying to do now. So let's use ODE 45. Should be okay. We have to create a function that he can use, func. We have to give him the time interval, time t from 0 to t max. And then we have to provide him with the initial values. Now you need one for each equation. How many equations did we have? I have j max minus 2. So the values I have to provide him, initial values, they range from 2 all the way up to j maximum minus 1. There I just pick the live, you might say, the live points that are unknown. Only the 19 in the mid of my channel, not the boundary conditions. So this will be the call to my ODE 45. Everybody with me so far? That's okay? No questions to this one? Okay. What do we get from the answer here? Well, we have, or maybe I shouldn't use y here. I use a big U. for the solution I obtained from ODE45. Much better, because I need y to something else. I need a vector giving the position of these velocities. So here I use linear space. Then I go from I go from -1 to 1, and I have j maximum of them. That should be correct. -2, of course, sorry. Then y is a linear vector giving my positions from wall to wall. That should be okay. And then we should be able to write simply plot, and I want the velocity in the x direction and the position in the y direction. That should be everything. But I have to create a function. So we need a new one. This function. Now he's going to return the time derivatives, du dt. This is just an internal name, so whatever you call him, that really doesn't matter. Just the name is only used inside this file. But now the next name has to be the name of the function file itself. And the standard notation for using ODE solvers, you have to have time and you have to have a vector inside here. So in all examples they always use t and y. We can do that as well. That's quite okay. Now in this function I'm going to need some values from the main program that I don't have. I have to know the number of unknowns, and also I'm going to need the delta y. I'm going to need those two. So I put them in a global sentence. Then again I give 0 vector here. That was j max and 1, like that. I do this because now I sort of start everything equal to 0 for all of them, also the first and the last. That's including the boundary conditions. That's important here. But from the ODE solver, when he's running, he's providing me here. These will now be the internal velocities from 2 to j max minus 1 at a given time. So here I have the internal field. He will be given. So now I have to duplicate that one into my u. So now I have something there already. So I have to say u from number 2 up to j max minus 1. They should be equal this y vector. Now I have a complete u field including the boundary conditions. Okay? If you don't like to do it like that, that would be one way. Another way, you could have said u equals, and then you could do something like this, 0, y, 0. That should also do the trick, actually. Create a new matrix or new vector, taking the one you get from him, and then give him 2 additional values. That would also work. Your choice. Then we have to calculate all the derivatives, all of them. Okay. How does it look? Well, the derivative, the equation were up here somewhere. I have this value k. Maybe we need him as well. Did I use him? Yes, I did. Okay. Let's put him in to the global here. Okay. Then the equation should read something like this. Okay. And then it was plus, and now the double derivative with respect to x written as finite difference. Finite difference. Okay, how do we make a double derivative? Well, we have used it here more or less, but now we have to think differently. You have to write it on a form that can be used in one single sentence. Now remember, this is 19 different values. It's a vector. How should you write the double derivative here? Well, first of all, it's going to be 1 over dy square. So he's definitely going to be there. What do we have inside here? Now comes the difference, finite difference. And what was the recipe? The recipe for a double derivative, that was u double equals I plus 1 minus 2 center point plus the other neighbor minus 1 divided by delta y square. So you need plus 1, minus 1, and then minus 2 of the center point. How can we write that? Well, you have to pick them from the vector itself. So here I want now number not from 2 to j max minus 1. You have to take 1 to the right. So they will be from number 3 all the way up to j max. And then minus 2 times the center, which will now read from 2 to j max minus 1, the internal points. And then finally plus u, and then the one starts with 1 all the way up to j max only. There you have written it sort of in a vector form. This is much faster than using a for loop. I could have done that as well, and then say the dt of I equals yada 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 and have a for loop. This one is much faster. So if possible, write your programs like this on a vector form. Not necessarily so easy. Here you have to sort of keep your bookkeeping right. So then I would recommend, don't care if it takes too long time. If you are more comfortable writing a for loop, you start with that. You do that first. Then later on, if you have time and you are interested, you can rewrite your for loops using vector notation. That's possible. So your choice. Here I use vector notation. So I save this one, call him func. So now let's see if the program runs. They never do. So what's wrong here? Let's see what he says. In an assignment, no, he didn't like that one. How come? I know what the error is. Anybody else? No, they're not equal, that's true. But the error here is more fundamental than that. And also here, MATLAB is terrible. You can't really tell from this expression here. You just say, as you stated, the vectors are not of equal size. And then you are inside a function. And sadly, inside a function, he don't remember what was in there when the program ends. So you can't really debug it afterwards. So it's a tricky one. The error is that one. I state in the function a global sentence. I want to have these values from the main program. Then the same global sentence has to be also in the main program. And you don't get a warning, you don't get an error. That's really bad for MATLAB. So I put the global sentence up here. And now we try to run it. Still not happy. What's wrong this time? Error in func line number 5. Okay. should still be okay. Minus. Thank you. That's something wrong here. Yes, he has to go. No. Thank you. Here we have it. Now they should be equal. Save. Go back and run. There we go. There we go. Now I chose TEP4280, sort of the first one you always use. That's the sort of the workhorse. 4th order accurate, very nice, and use the 5th order to assure that. But you see how he works, how many solutions that he has given you. Of course, you can say now, this is hilarious, I don't need all these solutions. What you then can do is simply in your main program, here you start from time 0 and end up with Tmax. There you can specify a time vector. So we start from time 0 with step 0.5 all the way 0.5 all the way up to Tmax. So instead of giving him just start and stop, you give him an entire timetable. Then you get solutions only at that times, and he will actually interpolate because he won't hit these specific times. He doesn't use a constant delta t, but he will provide you with this table if you ask for it. So that's one trick. That's quite convenient to know about. So now it's for every 0.5. So then you don't overflow your brain with solutions. Now instead, let's go back and leave it like it was, TEP4280. I mean, he's pretty fast if you think of what he's actually doing. There's 19 differential equations, many time steps, but he still operates quite nicely. You can play around if you like, just increase the number, Jmax, and see what happens. Now, for the stability, what about that one? For the FTCS scheme, we could have used this delta t. That was the absolute limit. R was 0.5. If I said 51 there, he exploded. What about TEP4280? He doesn't explode, but it's getting darker. He needs more time steps. And if you really push him, I think you're in trouble here. Let's try it. Remove a 0. 10 times as big. He made it actually. But you see, he needs many time steps to find a solution. What about the other solvers that we had? We had something used specifically for stiff solvers. Now switch from this one to ODE, say 23S, and see what happens. He doesn't need that many time steps. So they are very efficient, these stiff solvers. He has to work quite intensely in the start. Something is happening there. But then he can use a fairly big time step actually to provide you with a solution. Now, does it fit? Is it correct? The solution that we had up here, well, then I have to go back to the same delta t, of course. And now I just stop him, say, after half a second. 0.5. So I stop there. And then down here I say hold on. Then I plot the profiles here in the same graph. That should be possible. Then should plot these with what do we use? Red circles. So let's see if this one runs. No, it didn't. Hold on, why didn't it? He destroy. I still have the 0. Now. So the last ones, they should hit exactly, and you see I am quite off actually. So they are not entirely precise. So my first order scheme, not that accurate actually. He hits the center quite nicely, but not the end. Now I actually assume there's something wrong here, isn't it? It should be better. Also, I don't believe that we have a slip velocity here. So I think the scale for the ODE solver is not correct, is it? It really can't be. No, it can't be. So here I need this one plus dy, and here plus 1 minus dy. Let's see if that helps. Yeah. So it was actually much better than I was afraid of. So then you see actually he hits the solution quite nicely. So because for this problem here, just looking at the steady state situation, that's dangerous. Everybody can find the steady state in the end. Here is a question, do we have the correct time development? So here you should then stop him after, for instance, half a second or something, just to see that you have the correct time development. So the first order fits very nicely with a, well, what do I have now? That's only second order accurate. We can go back to 45. ODE 45. And you see the last one again fits very nicely. Any questions to that one? That's okay. The way I have done it here now is solving the Poisson equation from wall to wall. That should be unnecessary because I know this problem is symmetric along the center line in between the two plates. So it's actually enough to solve it only using half. So let's call this one something else. Call it Poisson half. I only want to solve half the problem. So we start from y equals 0 to 1. So now I skip the ODE solver. Remove that one. And this one. So now we are back to only the main problem. Like that. I reduced the number from 21 to 11. Why, if you want an even number, of course you can. Normally I use one extra, so to have sort of the boundary conditions there, but it really doesn't matter. So now the rest of the program should be as before, shouldn't it? The only problem now will be the boundary conditions. Because now I've changed one of the boundaries. I still have at position 1, you have a solid wall, 0. But this one should now read derivative equal to 0. So I have to write him like this. Sub x in position 0 should be 0. Derivative equal to 0. That's the boundary condition. So how do we do that one? Well, the internal field will be as before, going all the way from 2 to j max minus 1. But now j number 1, he's on the center. There I want the derivative equal to 0. How can I do that? How can I do that? So this is now my problem, one solid wall, and here I have a symmetry line. So my y-axis goes from 0 to 1, and I should get a solution looking something like this. Derivative equal to 0. I have one point here. That's my first point, the second point, third, and so on, all the way up to j max up here, which then is the other boundary condition. So the problem is this guy, how to have a derivative equal to 0 here. Because if you think in terms of central differencing, we are going to need something inside down here, outside our computational domain. Yes, you could use sort of what we call a ghost cell, one point outside your domain. Of course, we don't calculate him because by the symmetry we know this guy equals to this one. So that would be one way to deal with it. Invent a point here equal to this one, and then use the same differential equation for this point as that we already have. That could be one way to do it. Well, we can actually try it, can't we? Here is my original, so I just copy that one up here. So new u number 1. What should he read? Well, he's the old one there. And then we need here plus number 1. That should be number 2. And here j minus 1 should then read 0, which is illegal. That's the guy down here. I don't have him. But then I say I'm using the derivative equal to 0. Then these two should be equal. So the number 0 is the same as number 2. Okay. Then I just remove him and say I want him twice. Then I have used the sort of the original differential equation in the boundary condition. So that would be one way to do it. You do a special discretization at the boundary point, including the derivative there. Let's see if this one runs. So one parenthesis too many, is it? Yeah. Let's see what happens. Yeah. Not entirely correct, is it? Because if I here continue, T maximum equals 3, wasn't it? Then he goes too far. So now we have to reduce this driving force in the problem. I think he should here only be 1, if I remember correctly. Where do we have K? Not even that one. What else do we have? Yeah, I think it was the driving force there. It has to... No, not even that one. Well, I can use the brake to find that one. This one is not correct anymore. Distance is 1, not 2. That's more like it. So yeah, this one seems to be running, providing me with a good solution. Yes. So what about the stability criteria now? Let's say it exploded when we went a little bit too far. Does it still do that? Yeah, it was a little shaky. So we have the same stability problems. We have to keep this R smaller than 1/2, so nothing there has changed. Like that. So that was one way to deal with it. Another way, more brutal, would now be to say I create a derivative at this point, but then I have to use sort of a forward difference here in space, not a central. I don't want to use these ghost cells here. I want to have a derivative at this point. Well, if you only use the two first one, you can't get that. You will get a derivative here 1/2 a cell away. So that's a little wrong, but does that matter? Let's try it. A little crude one here. Remove this one. And then I say the number 1 equals the old one, number 2. Then I say derivative 1/2 a cell away from the center line equals to 0. And now I go back to 0.5. Let's see if this one runs. Yeah, he runs, but it looks a little strange. And I don't get the correct steady state solution. So here something is wrong.
Shouldn't the y vector go from 0 to 1 and not -1?
Where is the y vector? This one?
Yeah.
Yeah, it should, but I don't use it, I think. I use it. Ah, yeah, because I plot it. Yeah, but he will plot the only existing ones, so it doesn't matter. But yes, you should actually. Here it was. Yeah, it's correct, but now I said axis, so yeah. And I have to change that one as well. There is more correct. Yeah, thank you. So no, this was not really the optimum choice, not a good one. So what else can we do? Well, you can enter the book, and you find recipes there for higher order derivatives. So you have one here saying u derivative at this point equals, then I have to look, what was it? 4 times u number 2 minus u number 3 divided by 3. So there you can create a higher order derivative here using a forward difference, but then you need more points. This is second order accurate at this point. You can find even higher order, then you need more points. So let's try that one. So then we say number 1 equals, here we need then 4 times number 2, and then it was minus number 3 divided by 3. Now he was unstable. I didn't ask him to be unstable. So what has happened? Well, the stability criteria that we found from the original equation here said all coefficients positive must be bigger than 1. R must be smaller than 1/2. But here I have another equation. So now you have sort of exactly the same way of thinking. What's the sum of the coefficients? 4/3 minus 1/3 equals 1. Sum of the coefficient is 1. Yes, you can use them. The sum of all the coefficients has to be positive. Well, then we are in deep trouble, aren't we? We have one that is negative. So here we only have to hope that the criteria that the stability actually will survive, that this method obviously doesn't work. Negative coefficients should explode no matter what. So here, to have a more correct solution, to more correct stability criteria, you have to use more advanced methods. You can't use these positive coefficients. So here you see I reduced the time step. Now this ratio is down to 0.4, and then it is stable. But I can't find it with this very simple positive coefficient method. So here you should then use, for Neumann, matrix methods, more advanced stability methods. Any questions? Then we take a break.